Hello, everyone. Welcome to the virtual SI session. If you guys don't know me, my name is Hassib, and I go to the first two sections of the class.
Hi everyone, my name is Shivanku and I go to the last two sections of every class, and yeah, we are the SI leaders for CS146 with Professor David Taylor.
All right, and our topics today is to cover some of the logistics of the virtual sessions. In a way, I'll go over what are we gonna do and what to expect in the session and how you should interact in the session. Then after that, the main goal for this session is to cover MST trees, what they are, why we need them, and how we come up with MST trees, and cover the two main algorithms to get it, Prims and Kruskal, and in the end cover a little bit about what's the difference between these two algorithms. So to begin, Shivanku will start with telling us a little bit about MST trees and why we need them, and how are we going to come up with them.
So hi everyone. So let's talk about what's a MST. So MST stands for minimum spanning tree. So I just wanted to get an idea, Hassib, what do you think by the name? What does minimum spanning tree mean?
Well, by the name, it's like it's a tree, right? Like the name tells me it's a tree, and
Okay.
it's a tree that spans, minimum spanning. So it's like maybe I have a graph and I want to be able to span the entire graph using this tree. And
Okay.
the word minimum, I think it should like indicate, oh, this is like the cheapest way to like span a tree, something like that.
Yeah, you're pretty accurate. So basically what we are trying to do is, if we are given a graph, so let's take this as an example on my screen. So let's say if we are given this graph and we want to obtain the minimum spanning tree. So minimum spanning tree is a tree is a subgraph in which we can reach every other node of the graph when we start from one of the nodes. So in this example, it can be that when we start from 0, we can reach every other node in this graph paying the minimum possible cost. So there can be multiple paths which can be associated with one node. For example, node 2 can be reached by either going from 0 or going from 1, right? So you can be in a situation where there's a node, it has multiple paths which are connected to it. So we try to minimize the cost of the spanning tree. So a natural question that comes up in mind is, why are we doing this? So Haseeb, do you have any practical example why we are doing this?
So there was this example that I read in the book for minimum spanning trees, and if you have a different one, you can mention it too. So the example was about circuits and how different components, or how they connect different components of circuits together using wires. And the people who are making the circuit, they want some type of algorithm to find the cheapest way to connect to all the components from like a specific component.
Yeah.
And meaning the cheapest way in that context really means the minimum amount of wires needed.
Exactly.
So that was like a real life example of where minimum spanning trees could be used.
Yeah. Also, if you guys are finding it difficult to imagine, so you can imagine something like a network, like an internet network. So you have different routers. So whenever we request a website, the request goes from our router to the server, which is another router which is located in some remote location. So the request goes from our router, then it takes hops to all the routers in between, and it tries to reach the server. So when we do all this, we try to follow the path which gives us the minimum cost, because we want our request to go quick and the response to come quick. right? So it's similar to the example that Hassib gave, that we want at all times to find the path which costs us minimum. So in this example, let's say if I need to go to 2, I'll see, okay, if I go from 0, it will cost me 2. If I go from 1, it will cost me 3. So I'm probably better off going from 0, right? So that is where minimum spanning tree is useful. So it has a lot of real life applications. We don't see all these applications, but they are happening behind the scenes. So all these algorithms which we'll be learning in graphs, Ditchcastra, Virtual, all these are real life algorithms which are actually being used in our daily lives. It's just that we don't see it because it's really at low level programming that it is being used. So yeah, Hassib, do you want to add anything before we jump to prims?
No, and yeah, what you mentioned was very good. I have nothing to add. Let's move on to the how can we come up with a minimum spanning tree.
Awesome.
By the way, I guess I know what I can add. For the minimum spanning trees, it's an important question that comes up in the final and in midterms. Usually, the common way of asking this question is just do the algorithm. But also, there is another way of asking this question that I've seen on the midterms is maybe the professor tells you, oh, it's in the middle, the algorithm is in the middle of running and it's at the specific node, and oh, finish it from that point. So those questions are important. They come up, and they come up in two forms: is either run the algorithm from the start or run the algorithm from the middle. All right, so what we have here so far is I want to run a couple examples about the disjoint sets forests. And what I'm going to do is I have this graph, and I want to be able to run through the edges and put it in disjoint sets, and run some of the common operations that disjoint sets have. So before I start, let me ask a question. What are what are two of the most important operations that disjoint sets data structures have? You guys can type the answers in the chat. So some of these important operations are find set and union. Those are the important operations that we have for disjoint sets. And throughout this example, we're gonna run both of them and see what happens. So the algorithm goes, I'm gonna just loop through all the edges, and every time I find the edge, I want to join the two vertices on the sides of these edges. But I only join if those two vertices are in the same disjoint set. So let's start by this edge first. There's really no specific order that these edges that need to go in. So I'm just going to start from the top, going down to all to get to all the edges. Before I do anything, though, I need to make sure that each vertex is a set. So I call an operation called make set, which takes each vertex and makes it a set on its own. And that's why I have this node on the right side. And also you can imagine these nodes as the nodes that have the edge pointing to itself. Okay, so I will start with this edge. This is the edge that I have it highlighted here. When I finish it, I'm just gonna delete it. So I'm gonna process this edge. My loop is going through all the edges. I have the edge from G to H. So what I'm gonna do right now is I'm gonna run, I need to check if G and H are in the same disjoint set. So the way I can find the way I can find where G belongs or where H belongs, I call find set on G, and I call find set on H. What should the answer be if I called find set on G? If anybody would like to answer. So the purpose of the find set operation, it's to tell me what's the parent in this disjoint set. And since G is a disjoint set by itself and it has no parent, it will be the parent. So if I call find set on G, it will give me G. And if I called find set on H, it will give me H, because clearly they are in two different disjoint sets. So since they are in two different disjoint sets, I'm going to call an operation called union, which tells me, oh, I'm going to put the two vertices together in one set. One of them will be the parent, and the other will be the child. So I'm going to call union on G and H, and it will be something like this. H will be the parent, and G will be the child. The reason we did it this way is just the way of the book. The book selects the second vertex as the parent. And here we had the edge GH, and the second one is H, so I'm just going to make H as the parent. And it's going to be this way. G will point to H, and now I have this joint set together. I processed this edge, so I'm going to get rid of it. Now, I'm going to process the edge GA, and again, I'm going to run find set on G. What should find set on G give me? Find set on G should give me H. That's correct, because that's what I'm saying is, tell me what's the parent of what's the root of the disjoint set that G exists in. G, the root of this disjoint set is H, so find set on G will give me H. What about find set on A? Here, calling find set on A should give me A2, because A is the root of its disjoint set. Now, since G and A are in different disjoint sets, what I'm going to do is I'm going to join them together. But here I have a different situation where the set that G and H are in is bigger than the set that A is in. So I'm going to have A join H, just because where G exists is bigger than the disjoint set of A. And that's a heuristic that we call join by weight. It's different than join by rank, but it's very similar in idea. So I'm going to join A to H. This way. So I process this edge, I'm going to get rid of it. And yeah. So I'm going to process the edge between A and H, and now we're going to start moving a little faster. Find set on A should give me what? It should give me H, because H is the root. Find set on H should also give me H, because H is the root. Now in this case, find set on A and H gives me the same item, which is H. That tells me that A and H are in the same disjoint set. So it doesn't make sense to call union on them. So I'm not going to do anything. I'm not going to call union because they are in the same set. So I'm done with this edge. Now let me process this one between H and F. So I'm going to call find set on H. It should give me back H because it's the root. I'm going to call find set on F, And what should find set on F give me? Which is this one. So find set on F should give me F because it is actually the root of itself, of its disjoint set. And all I'm gonna do is join it to the bigger set this way. And I'm done with this edge. Then let me process the edge between A and B. Again, the same logic. I'm gonna call find set on A, and A is right here. Find set on A should give me the root of its disjoint set, and the root of this disjoint set is H. So A is an H, okay? Then I wanna call find set on B. B is right here, and it's by itself. So do A and B have different disjoint sets? Well, clearly they do. So I'm gonna call union on them. And since H is bigger, I'm joining B to the disjoint set of H. And just to keep in mind here, we're not doing any work for minimum spanning trees. We're just examining the disjoint set data structure and see how it's working. So I processed this edge, I get rid of it. Now I have the edge between B and F. I call find set on B. B tells me that I'm in the set of H. I call find set on F. F tells me that I'm in the set of H. I realize that B and H are in the same disjoint set, so it doesn't make sense to run join on them because they're in the same set. So I get rid of it. I'm done with that edge. This one is hidden. So I process AC. Again, there's no specific order that I'm taking the edges in. I call find set on A. This is A right here, and it's in the disjoint set of H, so it gives me H. I call find set on C. C is here, and C is by itself, so C gives me C. So I notice that C and A are in different disjoint sets, so I union them, and that means C will join H. Now I'm done with this edge. Now I have this edge, CB. I call find set on C, it gives me H. I call find set on B, it gives me H. They're in the same disjoint set. Union will not do anything. So I'm not going to call union. I have CF. I have this edge. I call find set on C, and it gives me H. I call find set on F, it gives me H. They're in the same disjoint set. It doesn't make sense to call union on them. I have DF. Now this one's gonna it's gonna change stuff a little bit. D is, I call find set on D, and it should return itself because it is in the disjoint set of D. Then I call find set on F, and that should give me H, because F in the disjoint set of H. I union them, I bring the smaller one to the bigger one. And I join D to F. And I'm done with this edge. Then I have another edge, FE. I call find set on F, it gives me H. I call find set on E, it gives me itself. They're in two different disjoint sets. I join them because I'm gonna call union. And now I notice that all my vertices are pointing to, or all my vertices exist in one disjoint set. So I can look at the graph and I go, oh, the probably processing the rest of the edges won't give me, won't run union at all because everything is in the same set. So if I took C and D, calling find set on C will give me H, calling find set on D will give me H. They're in the same disjoint set. Nothing will happen. I'm not going to call union. D and E, calling find set on D will give me H, calling find set on E will give me H. Nothing will happen. They're in the same disjoint set, and that's the same situation for C and D. This will not do anything. So we can notice that if the vertices of my graph are all connected, eventually they will all make it to disjoint to one disjoint set. And what the disjoint sets here do to us is, in a way, categorize vertices in one group. So let's say we had a graph that had like two separate components, and we try to run the disjoint set algorithm. What the disjoint set algorithm will give us back is two disjoint sets telling me that this node is part of this component, or this node is part of another component. That's only if the graph had maybe two or more components. But here, since all the vertices were connected, I got everything in the same disjoint set. So the point here is there's two important operations in the disjoint set data structure, which is find set and union. Kruskal's algorithm is an algorithm for us to find the minimum spanning tree. And internally, it uses the disjoint set data structure. And it starts with the following. We're gonna run through all the vertices, and I'm gonna make a set out of each vertex. So I'm gonna get a situation like this, just like what we had before here, but for this graph on the left. And I'm gonna make set out of each vertex. So I get each vertex as a disjoint set by itself. So that's the first step of the algorithm. The second step of the algorithm tells me, take the edges in descending order and process them the same way we did here. So what we did in this algorithm is we just took the edges in arbitrary order, in whatever order I wanted to. There's no specified order. And we also can notice that the edges here did not have weights. Here, since the edges have weights, I'm going to take the edges in descending order. That's how Kruskal works. I'm going to take the edges in descending order in order for me to find the minimum spanning tree. So looking at this graph, and here what I have is the list of edges with their weights. Which edge should I start with? I have a sum of edges, and my algorithm tells me that I need to start with the edges of descending order. So I can notice that there is two edges of weight 1. I can start with any one of them. So the edge AC could work, or if I start with the edge BF, that could work too. And as long as I start with the edges in non-decreasing order, that's really the technical word that the algorithm uses, is we're gonna get the edges in non-decreasing order, which is not technically the same as increasing, but also tells me that if I have two numbers of 1 or 2 edges of weight 1, I'll just start with any one of them, as long as I make sure I finish them first. So I'm going to start with CA, and I'm going to process it. So CA is this one right here. I'm going to run something similar to what we were doing a couple minutes ahead before, which is find set on A. So if I ran find set on A, what should that give me? So find set should tells me what's the root of the disjoint set that I'm in, and find set on A should therefore return A because it's the root of its disjoint set. What about find set on C? C is a similar situation to A. It's by itself, so it's gonna give me C. So what I notice is A and C, they're in two different sets. I'm gonna call union on them. So, and the way the algorithm works, or the way union works from what we saw before on this example, is that I'm going to make the second one as the parent because both of them are the same size. So C becomes the parent. And it will, C becomes the parent and A will point to C. So I process this edge. What I'm going to do, since it's an edge that caused me to do a union, I'm just going to color it with red. This is an edge that caused a union. Okay, so we're done with this edge. I'm gonna put a star next to it, so I mark it as we're done. What's the next edge that I need to process? As we mentioned before, we're going through a non-decreasing order. So, and doesn't matter which one we start with. So I'm gonna go with the edge BF. So BF, I go to that edge in the graph. It's this one, and I call find set on B. We saw that happening a little bit. We saw that just happening. B should give me B. Then I call find set on F. F is by itself, so it should give me F. Then I'm gonna make the second one as the parent, which is the second one in this pair, the F as the parent, and I call union on both of them. So F becomes the parent, and I make B point to F. Okay, so I processed this one. This edge caused a union, so I'm just gonna color it with red because that's gonna be important to me later on. All right, what's the edge that we need to process after? So I have one. Then if I looked at the weights, I will notice that the edge that I need to process after is ED. I have a question, which is why did I start at AC and I did not start at CB? Well, the edge CB has a weight of 17, and we need to start with we need to take our edges in non-decreasing order, which is starting from the smallest going to the biggest. So in terms of weights, so I finished the edges with weight 1. I finished this edge with weight 1. What's the next number? The next smallest weight is 3. So I'm gonna start processing ED. So if I want to process ED is right here, and I'm gonna call find set on E. E is by itself, so it should give me E. I'm going to call find set on D, D by itself, so it should give me D. And since they're only one, I'm going to make the second vertex as a parent. So who becomes the parent then? In this case, since D came second, D becomes the parent. So E will point at D as the root of its disjoint set. So this this edge caused the union, so I'm going to highlight it too. All right, so what's the next edge? Here, GH, which is 4, we're taking the edges in non-decreasing order. Again, we have to remember here that this is a little different than prims, where prims we take a vertex and we run through its vertices. But in Kruskal, we don't take a vertex and run through vertices, we just take vertices right away. So the next vertex, or we just take edges right away. We don't take vertices and run through its edges. We just take the edges in non-decreasing order. So the next edge that we need to take is 4, because that's the next smallest edge after we finished 3. So I call find set on G. G's right here, and this is the edge. I call find set on G. G's by itself. We saw this a couple times, so it should give me G. I call find set on H. H is by itself, so that should give me H. But my question right now is, who's going to become the parent? And it's really doesn't really matter, but the way the book does it is that the second vertex and that edge will be the parent. So in this case, it's H. So H becomes the parent, and I make G point to H. Okay, this is an edge that caused the union, so I'm going to highlight it with red. All right, let me go through the edge after. We mark 4 as done, and it looks like we're processing CE because it's the next smallest edge. So CE is this one. This is the big one. And this is an edge of weight 5. What I'm going to do is, I'm going to call find set on C. What should find set on C give me? Find set on C should give me C, because C is in the disjoint set of C. So it will give me C. Then I want to call find set on E. E is in the disjoint set of D. So find set on E will give me D. Again, I'm going to run through this again. Find set on C should give me C, because C is in the disjoint set of C. C is the root of this disjoint set. So when I call find set on it, it should give me that root. Then E, when I call find set on E, E goes, oh, I'm going to give you the root of my disjoint set, which is D. So I get D because of find set on E. Because of that, I realized that those two C and E exist in 2 different disjoint sets. So I'm going to call union on them. That means this edge caused a union. Now we look at these and we go, oh, they look the same, and they have something called rank, and they have the same rank because this one have a rank of 1, this one has a rank of 1. That's just because we added only one edge to it. So if they are the same, the book goes, we're just going to make the second one as the parent. So making E as the parent, but it's not technically E. It's making the root of E as the parent. So this will cause this union. C will point at D. This is very important to notice. Although we're saying that it's E that's going to be the parent, but it's technically we need to point at the root of the disjoint set of E. So find set on E gave me D, so D is going to be the parent. So we can see the graph coming together. This edge caused a union, so I'm going to give it a red color. And I'm going to process the next edge. What's the next edge that I need to go over after CE? So here in our edges, the next edge that I need to touch on is the next smallest edge, which is HF. It has 7. Here we processed this one already. We forgot to mark it. So 7, it's HF. I look at the graph and HF is right here. I call find set on H, and that's the same situation that happened with us with the C. We called find set on C and it gave us C because it is actually the root. I call find set on H, it gives me H. I call find set on F, also the same situation, that gives me F. So they're the same trees, they have the same rank. So the second one becomes the parent. That means the root of F becomes the parent, but it is the root, so it becomes the parent. And I'm just gonna have H point to it. This way. Okay. This is bigger, this is B. All right, so what we saw so far is a couple unions. We ran find set multiple times for every time we are processing an edge. But something we did not talk about is the idea of rank. So to begin with, all the vertices start with a rank of 0. And every time we call a union, we increase the rank of the parent. So we made a union on G and F initially without the rest. That's just the first operation of union on G and F. That made the rank for H equal to 1. Then we just ran a union between F and B and H and G. H had a union of H had a rank of 1, F had a rank of 1. So when we called union of them, and the disjoint set of F of H became the child of the disjoint set of F. Because of that, we increased the rank of F. The rank of F was 1. Now the rank of F is 2. I'm not writing anything down as far as the rank, because that's one way that I can keep you guys remembering what's happening in the graph. So F has a rank of 2 because we joined 2 disjoint sets of rank 1, and since F became the parent, I need to increase its rank. It's the same situation here with the one with D. D has a rank of 2 again, and we can notice that they have the same shape. So D has a rank of 2 also. When it comes to rank, I only care about the rank of the root. I don't care about the rank of whatever inside that disjoint set. All right, so let's finish our edges. I just processed the edge of weight 7. What edge should I process after? So after 7, we have the next smallest edge is 8. So it's CF. Let me identify it in the graph. CF is this long one. And oh, I think we forgot something. H and F caused the union. So I just need to give it a color red. So I'm processing CF. I need to call find set on C. C is this one. Find set on C should give me the root of that disjoint set, and that should give me D. Then I call find set on F. F is the root of its disjoint set, so I just get F. And what that tells me is C and F are in 2 different disjoint sets, so I'm going to call union on them. I run into the same situation where both of them have the same rank. So again, the way we break this tie is by making the second one as a parent. So I just have D point to F this way. And let me make it look a little more like a tree. I'm going to shift them down a little bit. This looks a little better. Okay. We lost the F. So I processed 8, the CF edge. This caused the union. I'm just going to color it with red. All right, what's the next edge to process? I'm going to mark 8 as done. And the next edge, which is the next smallest edge, and that would be the edge DF. DF is this one right here with a weight of 9. I do the same logic. I call find set on D. D is directly connected to F, and D will give me F. And because of what we did, to go back a little bit, the CF edge, it caused the union. It caused the union between two disjoint sets of the same rank. And since we made F as the parent, we need to increase the rank of F. So it went from 2 to 3. So whoever noticed this, the idea about the rank that I missed, yes, you are correct. So the rank of F will be 3 right now, just because it became the parent, and therefore we need to increase its rank. So again, we go back to the process we were doing. We called find set on D, that gave me F. We called find set on F, it is the root, so it will bring back F. And that tells me D and F are in the same disjoint set. So I'm not going to call union on them because it doesn't make sense to call union on them. So this edge did not cause a union. So I'm not going to color it with red. All right, so I finished this one. What's the next edge that I need to process? And I need to look for the next smallest edge. And the next smallest edge looks like it's 10, and it's AB. So I look at AB, it's this one. And I call find set on A. A is here. And that's where some interesting stuff happens. A looks up, it's C, C still has a parent, it looks up, it's D, D still has a parent, so it looks up, it's F. We got to the root, and find set on A should give me F. Well, when we run this find set operation, we notice that we're doing a lot of jumps, and there's a heuristic that we can do to minimize the future work to when we run find set on A, which is something called path compression. So the idea here is when I run find set on A, and I'm going all the way up to find the root, while I'm going up, I'm going to make all the nodes in my way point to that root directly. So I'm running find set on A, I'm going up, I get to C, I'm going up, I get to D, and from D I go up, I get F. Since this is a recursive operation, like the answer, which is F, which is what we're looking for, will like propagate down to A, and then we get the answer because we're calling find set on A. So A will go up, we'll get to F, F is the root, then I send the answer back, and the answer propagates downwards until we hit A, and I get the answer F. So because of this operation, what I would do on when the answer is coming back is I'm going to set the parent of each of these nodes to be that answer. So the answer, which is F, when I say the answer, it's the answer of the find set operation. When the answer is F, so it's going down, it hits D. I make D's parent F. That means it's the same, nothing changes. Then the answer hits C. and I go, oh, I'm going to make C's parent F. So C starts pointing at F. Then the answer is still coming down to A. And what I'm going to do is A's parent becomes F. I got a little messy in here. And that's path compression. So what we did here is, since we called find path on an edge, on a vertice that is not directly connected to the root, I'm just going to make it connected directly to the root. So the next time I call find set on A, it's only one step to get to the root. That's called path compression. And this example will result of quite a bit of these operations. Now, okay, let's get back to processing the edge. We were at edge AB. So I called find set on A. It gives me F, and this is a find set operation that caused some path compression. It will improve the performance for future operations only, and that gave me F. I call find set on F on B, and that should give me F because it's the root. And now, am I going to make a union between A and F? Should I call union between A and F? And the reason I can figure it out, or the way I can figure it out, is A gave me F, find set on A gave me F, and find set on B gave me F. That means they are in the same disjoint set. I'm not going to call union because it doesn't make sense to call union on two vertices that are in the same disjoint set. It's the same situation that we have here. We noticed so far that all our vertices are in the same disjoint set, so we kind of know that there will be no unions. This edge AB did not cause a union, so I'm not going to color it red. I processed 10, and I'm going to move on to the next smallest. The next smallest after 10 looks like it's the 13. 13 is CD. I call find set on C. C points directly to F. No path compression will happen. So I'll just get F. Then I'll call find set on D. D gives me F. No path compression happens. And those are in the same disjoint set. So no union. I'm not going to color it red. And I'm going to start moving a little quickly because it starts becoming the same logic. So we processed 13. It's done. The next smallest is 15. E and F. I call find set on E. And E should give me F because that's the root of its disjoint set. But is path compression is going to happen when I call find set on E? My question is, will a path compression happen when I call find set on E? And since E is not pointing directly to F, that means I need to make it point directly to F, and that's what path compression is. So E, instead of pointing directly to F and pointing to D, it will start pointing directly to F. And again, this got pretty messy. So now I did path compression. E gives me F, and I call find set on F. That should gives me F. So they are in the same set. Doesn't make sense to call union. I'm not going to color it red. So I just processed F, EF, which is weight 15. The next one to process is 16, AG. Now I'm going to call find set on A, gives me F, no path compression. I'm going to call find set on G. G is right here. G is not pointing directly to F, so that's going to cause some path compression. So it's going to point directly at F. And it should return F. What is happening here? I want to know what's inside this edge. Okay, this is an H. All right, so I called find set on G, it gave me F. I called find set on A, it gave me F. They are in the same disjoint set. I'm not going to union, but I just need to notice that I had to do some path compression on G. And I'm not going to color it red because it did not cause a union. All right, I process this one. Then the last two edges is AH. AH is this one right here. I call find set on A, directly connected to F, no path compression. I get F. I call find set on H, directly connected to F, no path compression. I know that they're in the same disjoint set, so I'm not going to call union. Therefore, I'm not going to color it red. So I'm done with this one. And I'm going to have the same situation for C and B. No path compression, no union, and I'm done with it. Then I look at my graph, and I colored some of them as red. And those are the edges that caused union. And the red edges is the minimum spanning tree. Is those edges that caused a union, and this is the cheapest way I can span this tree. And if you noticed that if you notice on the graph, you'll see that all the edges have small weights, and that tells me that this is the cheapest way I can span this graph that I have. So Prims versus Kruskal. From Shivanku earlier ran the Prims algorithm, and from what we saw on the visualization, it wasn't clear what internal data structure was Prims using, but Shivanku did mention that it's a minimum priority queue. So for Prim's algorithm, the internal data structure is a queue. Specifically, it's a minimum priority queue. And for Prim's algorithm, we need a source node. We need to start the algorithm, telling the algorithm, I want to start the minimum spanning tree from like A or B, just whatever source it is. I need to specify a source. However, when it comes to Kruskal, the differences between Kruskal and Prims is that Kruskal uses a disjoint set forest data structure internally. And that's what we were doing earlier in the graph, is we're representing the different disjoint sets, and we're doing operations on it. So it uses that data structures internally. And for Kruskal, we don't need a source node. Those are the two differences between Prims and Kruskal. Again, I remember from my midterm that both questions came up, Prims and Kruskal, on the same midterm. The questions were either run the algorithm, and here's a graph, and run the algorithm, or here is a graph, and you are in the middle of running the algorithm. So it's very important concepts to touch over.